Alright, so hey guys, so this video is going to be on decision trees. It's going to be the first of two videos on decision trees, and we're just basically going to introduce decision trees and then talk about some of the mathematical concepts that are used in order to actually create a decision tree. But first, let's just talk about what is a decision tree, right? So, the decision trees that we're going to be talking about in the series of lectures are going to be used for classification, right? So, a lot of machine learning problems require you to distinguish, given some sort of object, is it in this group or that group, or any number of groups, right? So, for example, in the competition that we're going to be providing or that we have provided in the past, um, one of the data sets basically had a lot of different features of tumor sizes, right? So this is like, what is the diameter of the tumor, how hard is the tumor, stuff like that. And you're supposed to determine, is it a malignant tumor, meaning that it's cancerous, or is it benign, meaning it's not harmful to the person who has it. And so it doesn't just have to be classifying something into two groups, it can be any number of groups. But basically, that is what a decision tree is. It's just a way, it's a classifier, right? It classifies different things into different groups. And so, in order to create a decision tree, you basically just have to figure out what are the right questions to ask, right? So, you have to figure out the because the decision tree is just a series of questions, and at each question you will fork into different groups. You either The goal is to create questions that split the data into the groups that you want as efficiently as possible, right? Because those are the questions that uh, cause you to gain the most information. I'm using terms from future parts of the lecture, but this is just an example of a decision tree that basically makes a decision. It's not really what you would find in like real machine learning tasks, but it's just a flow chart, if you will, to determine, okay, what should I do now, right? So if you have work, you can see these questions, and it makes sense. Each sort of node in the decision tree, we split into two forks, and then depending on the answer to the question, right? And so this is essentially what a decision tree is. It's just a series of questions that you ask that somehow splits the data into different groups. And the art of creating a good decision tree is figuring out what are the right questions to ask. So there are basically two main formula. I won't discuss them now. I'll discuss them actually through an example. So let's just get into the example straight away. So imagine we have a data set of athletes, right? And these athletes are either tennis players or basketball players. And we have data about each of these athletes, specifically their age and their height. And so our goal is to differentiate the tennis players from the basketball players as best as possible. And so we want to create a decision tree. Actually, for this example, we're not creating a whole decision tree. We are actually just doing one layer of the decision tree. So we're trying to figure out what is the best question to ask from when we start off. And so this is our original data set. It's repeated on both the left and right hand side. So each of the T's stands for a tennis player, and each of the B's stands for a basketball player, right? And so, there are 3 tennis players and there's 3 basketball players. So an even split. And we want to basically find which of the questions that I've listed here does the best job of accomplishing our goal, which is to split the tennis players from the basketball players as well as possible, right? The 2 questions that we have are, is age greater than 27? And then, is your height greater than 6 feet and 4 inches? So, just by just by thinking about this, you could imagine, I mean, there's no real, at least in my mind, there's no real reason why, basketball players should be older or younger than tennis players. So, asking the first question probably doesn't really make much sense. But for the second question, it does make sense. Um, I think if you're taller, you're more likely to enjoy playing basketball because you're better at it, right? So maybe there is something there. And if we actually look at what happens when we ask these questions on the data, you can see um, which question is better, right? So if you look here, um, sorry, I did not include this before. But basically, all of the things on the right hand side satisfy this question, and all the things on the left hand side do not meet this requirement, right? So all of these athletes on the right hand side of the of of this part, they are older than 27, and all the players here, or all the athletes here, are not older than 27. And similarly, uh, all the players here on this right hand side are 6'4", or they're taller than 6'4", and all the athletes here are shorter than 6'4", right? That's what the yes, that's what the Y and N signify. Did yes or no for each of the questions. And so you can already tell just by looking at how the data was split that this right hand question, is height greater than 6 feet 4 inches? That did a better job of splitting the data compared to this other question, right? I mean, it just looks better because there's, most of the most of the athletes on the right hand side of this diagram are basketball players, and all of the athletes here are on the left hand side are tennis players. Whereas here there's a bit more of a mix. But we can tell, using ourselves, but the goal is to get the computer to do this. So we have to somehow mathematically define what each of these, we have to come up with the algorithm for finding the best feature or best question to split on. And so this is where the two main ideas of this lecture are going to come in. One is Gini impurity, and the other is information gain. Okay, so first we're going to do Gini impurity because you need the impurity in order to calculate information gain. So we're going to start off with the prerequisite, if that makes sense. So let's first calculate the impurity of the starting data set. So that's this, basically. And the formula for Gini impurity, which is one type of impurity, there's actually two main ones, but we're just going to be focusing on this one, is this. So this may look complicated, especially if you're not familiar with like sigma notation and stuff, but all this is saying is for each of the classes in a certain like part of this decision tree, for all the data values, just calculate the probability of that class, square it, and subtract it from 1 for each class. And if that doesn't seem clear, don't worry, we're just going to walk through an example and you'll see it's very simple. So let's do this for here. Let's calculate the impurity for this part of the data in this node, right? So we start off 1 minus, right? And then we now do the sigma notation, which is sums over all the classes in this data. So there are two classes here, right? Basketball and tennis. And so first we calculate, okay, what's the probability that if I randomly select, some athlete from this group, the circled group, what's the probability that they play basketball? Well, that's just 3/6, right? And we square it, and we also, it's going to be the same thing for the tennis player, right? It's 3/6. And so now we can just calculate it like this. And so this is going to be 1 minus 1/4 minus 1/4, which is equal to 1/2, right? Pretty simple. So the impurity here in this starting data is 0.5. And this actually is the maximum impurity possible, right? This is like the most impure you can get, right? Because they're both equal in the amount of um, each class has an equal number of elements. So there's three tennis players and there's three basketball players, so you can't really get more impure than that. So now let's go calculate the impurity for both of the data sets, for all four of these. This one, this one, this one, and this one. We already calculated this one because it's the same as the circle data set here. So this is also 1/2. And so now let's calculate the Gini impurity for this group. And you can probably, it's probably helpful if you also do it at, like pause the video and then try it out. It's pretty simple, so give it a try. So for this one, it's going to be 1 minus, okay, let's do the tennis players first. So there's one tennis player out of the three athletes. So the probability that you pick a tennis player from this group is going to be 1/3. Square that and do the same thing for the basketball players. That's just going to be 2/3. And then you get 1 minus 1/9 minus 4/9, which is going to be 4/9. And doing the same thing for here is going to be actually the same calculation, but I'll just do it again. So first, let's do the tennis players first. It's going to be 1 minus 2/3 squared, right? Because there's two tennis players out of three total athletes. And then there's going to be one basketball player. So that's going to be 1/3 squared here. And then when you do this, you'll also get 4/9. Okay, so I'll just write that very close to the results here. And we'll clean this up. And so we do the same thing here. So these two groups of data are a bit more interesting. So we can do this, we can calculate the impurity here. There's only one group here, right? Tennis players. And there are two tennis players, and there's only two total, right? So the probability that you pick a tennis player is 2 out of 2, or just 1. And so the impurity here is 0. And this is actually the minimum possible impurity, right? You can't get more pure than having all of the same class, right? This is basically like a perfect node. We have classified, like, you can't get better than this. This is a bit more, there's obviously still, on the right hand side, there's a tennis player in there. So it's not perfect, but it's still going to be pretty low. So let's first do the tennis player. So that's going to be 1/4, right? Because there's one tennis player and four total players. And then for basketball, it's going to be 3/4. And so if you do this, it's going to be 1 minus 1/16 minus 9/16. And this is going to be, okay, so 6/16 or just 3/8. Right? And so we can write that result here, and I'll write this result here, and this was 3/8. And erase everything here. Okay, so now we have the impurities for all the different nodes in both of our kind of mini decision trees, right? So now what we can do is actually talk about information gain, which determines, okay, which of these two questions is a better question to ask. The information gain formula is here. Here the I that you see here and here and here represents impurity, and for us this is Gini, this was Gini impurity, and n just represents the number of elements in each of these nodes, right? And so we can walk through this example. So let's calculate the information gain that results from this, asking this question of whether or not the age was greater than 27. So first we start off with the parent node's impurity, which was 1/2. And then we basically find out, okay, how many different elements were in this group. So that was 3. And how many were in the parent group? That was 6. And going back to the formula, that's just this term right here. That's just this term, right? So n left is the number of elements that resulted in the left node, and then np is a number of elements that were originally in the parent node. And so this is basically like weighting each of the impurities by the number of elements that are in that node, right? And the impurity for this left node, as we calculated before, was 4/9. And then we do the same thing for the right node. So there were 3 elements here, right? So this is also going to be 3/6. Let me just put parentheses around this. And then the impurity was also 4/9. And so I did these calculations beforehand just so it would not be too messy. But this results in an information gain of 0.0556. Right? Okay, and so now let's do the other side so we have something to compare it to. So we can calculate the information gain for this side as well, right? So the original parent node impurity was the same as before, it's just 1/2. And then we subtract, okay, so how many items were in this left node? That was just 2, and then the number of elements in the parent node were 6. And then what was the impurity of the left node? Well, we found out that was 0, right? It was perfectly pure. And then on the right side, there were 4 elements in the right node, and then the impurity was 3/8. And so if you carry this out, this is actually, we can do it ourselves. This is just, these two cancel out to be, this whole thing becomes 1/4. And so, 1/2 minus 1/4 is just 1/4, or 0.25. And so you can kind of see, 0.25, which was the information gain from asking this question, from the right-hand question, is greater than 0.0556, which is the information gain that resulted from asking the left question, is age greater than 27? And so this means that asking the question about height is actually a better question than asking about age. Information gain, the higher the information gain, the better the question. And so when you're creating an actual decision tree, I just did sort of one step of this decision tree, but in practice, what you would do is you would continue until you would keep going until all the nodes are completely pure. Now, there is you shouldn't do this. You shouldn't actually do this because this can lead to overfitting, but that's sort of like the algorithm that's stated. There's ways to combat overfitting that I'll talk about in part 2, but basically, whatever the whole process that we just did for determining these questions, you would just do for each of the child nodes as well, right? So just like how we treated this as the parent node, once you are done with this layer, since this is already pure, since the left-hand side is already pure, you would go on to this node and treat it as a parent node, and then try to figure out, okay, what's another question that I could ask, right? In this data set, I only talked about two different features, like is height greater than 6'4" and is age greater than 27. In real world data, you'll have many more possible things to ask, right? For example, in the competition that we have about the cancer tumors that I talked about earlier, there's 10 different features that you can split on, and there's many different values in the data set that you can ask. Oh, and that's something I didn't really talk about in this lecture, but I'll talk about in the next lecture. So the way you actually get like this number, you basically try out different values in your data set that you use for training. So what you can do is like, um, let's say some of these players, the heights for these players were like 5'1", 6'2", 6'3", 6'4", um, um, 5'10", and then 6'1" or something. I just made those up, but for you would basically try out each of those values for this field here, like this field, and similar thing for age. You try out all of the different ages of the players for this value here that you use to split on. And then in order to figure out, okay, like what do I ask here, you just iterate over all the different sort of features that you have in your data set, right? So maybe another thing that was in your data set was like, what brand are these players sponsored by? And maybe, like basketball players are more likely to be sponsored by, I don't know, um, Nike, and then tennis players are more likely to be sponsored by Adidas or something, right? And so you could ask, another question that you could ask is, okay, is the brand Adidas or is the brand Nike? That's a sort of different question than we have here, but that's a totally like doable thing too. You just have to like convert that to numerical form. Um, and so yeah, um, I'll talk more about like implementation details in part two. But this was Decision Trees part one. Thank you.